this class, we learn about the template design pattern. Again, this is a very commonly used design pattern, especially if you're integrating with pre-designed frameworks or any of the standard libraries. The template pattern is used widely to provide the programmer a level of customization within very complicated algorithms. So, what does this template pattern actually do? Say you're writing code to achieve some objective. You have an algorithm you follow to write this bit of code. It's often the case that there are many ways of solving the same problem. All of these ways have the same series of steps, but they differ perhaps in one piece of logic or one section of code. This is a very common use case. Now, say you were to write code to achieve this objective, there are one of two things you can do. The first option is you write code to solve this problem completely from scratch. Every bit of code you write yourself. This is not always a great solution. This means you have to test every corner case in your code and you're kind of reinventing the wheel. The other option you have is you use some pre-canned algorithm which does what you want it to do. This is again not a great option. Why is that? This is because the pre-canned algorithm may not follow all the steps that you want. It will be 90% of what you want, but the 10% you want something different which you won't get using the pre-canned algorithm. This is where the template pattern steps in. The template pattern basically defines a series of steps for the algorithm to follow, and it will have implementations for all of the steps. However, it will allow you as a programmer to hook in to certain portions of the code and provide your own customizations. This way, you form a happy medium between writing your code from scratch and using a pre-existing algorithm. You're allowed to you don't need to do everything yourself. You don't have to use someone else's code. You can customize exactly the bits which you want to. Let's see where this template pattern is useful. As programming languages have gotten more and more powerful, programmers tend to spend less and less time on the little stuff, the nitty-gritty details of what they're supposed to do in each logical unit, and more time on the big stuff. The big stuff meaning pulling all these logical units together to achieve a really complicated and difficult objective. This means you don't worry about the little details and nitty-gritty. You assume libraries will take care of that for you, and you focus on high-level programming. More high-level programming, less low-level programming. That's the trend in computer science over the last few decades. In fact, this is logical because it is this trend which allows us to write even more complex systems built on the shoulders of systems which came before us. The libraries dealing with the nitty-gritty like network connections, UI rendering, so on and so forth. If we had to code everything from scratch, we'd basically not be able to accomplish much. But using these logical blocks make us write complicated code and build complex systems with much more ease. And how do you accomplish this high-level stuff that you're set out to do? More and more of this high-level stuff is done by using frameworks. Frameworks are existing systems of complicated groups of classes that accomplish an objective. They provide a whole bunch of logical components which help you get things done. They do a bunch of stuff themselves, and as a programmer who's integrating with a framework, your job is to plug in little bits of code that customize what the framework does. The framework takes care of the majority of the work behind the scenes. You plug in customizations in different portions of the framework to accomplish exactly what you want. Your high-level work is done by using frameworks. Frameworks provided a whole bunch of libraries which allow you to customize and build exactly what you need. Frameworks. These widely use something known as the dependency inversion principle. Let's look at the definition of dependency inversion principle. Let me just warn you that there's a lot of verbiage in there. I'll try to break it down for you. Basically, what the dependency inversion principle means is that there are a whole bunch of low-level components which are individual units performing specific tasks. You have high-level components which use these low-level components to achieve a bigger objective. Now, these high-level components should be completely independent of the implementation details of the low-level components. They should not depend on the low-level modules. They should only use the abstractions which the low-level components provide and work completely independently of the implementation details. Alright, was that too much for you? Let's try to state it in simply one line. You can say that high-level code says to low-level code, which takes care of the nitty-gritty, don't call us, we'll call you. Basically, the high-level code tells low-level code, we will call you to get our job done, do not call us. This is the dependency inversion principle. And frameworks built on principles are a natural extension of the template pattern. One quick FYI before I move into what the template pattern is and describing it in more detail. The template pattern doesn't have anything to do with generic classes or templated containers. They are completely different even though they seem to share a name. Templates or generics are a way to instantiate the same class using different types, templated types. Template pattern has nothing to do with that. In the template pattern, typically a very complicated algorithm is implemented. The complete implementation can be provided in the form of steps. So you can imagine a whole bunch of methods taking care of step 1, step 2, step 3, etc. of this complicated algorithm. And these steps are called one after the other. Now, this complicated algorithm is implemented in the form of an instantiated method of an abstract base class. What does this mean? This means that you have an abstract base class. It has a whole bunch of methods. Most of these methods have implementations. These implementations are the various steps in the complicated algorithm which are pre-implemented for us as a form of instantiated methods of this abstract base class. Instantiated methods basically just mean methods which have implementation. Now, the programmer simply has to plug in the customizations to specific steps. Now, in this entire series of steps which define the algorithm, some are implemented, some are virtual methods. By implementing the abstract methods of the abstract base class, we simply provide customizations to this entire series of steps which make up the algorithm. This abstract base class, which has the series of steps which make up the algorithm, is a template for the complicated operation. The steps in the abstract base class provide the template. Implemented methods are the template. Customizations are specified by the abstract or the unimplemented methods in this abstract base class. So all the unimplemented methods in the series of steps which complete the algorithm are left for the programmer. And these are called hooks. So a template pattern is made up of a template, which is the series of steps, and hooks, where a programmer can plug in his customizations. This combination of template and hooks allows a nice medium where a programmer doesn't completely have to rely on a pre-canned algorithm provided by someone else. He's allowed to customize the interesting and the complicated bits using hooks. Let's see a logical example of the template pattern at work. Say we want to specify an algorithm which does text auto summarization. Basically, this algorithm takes in a long piece of text and summarizes it. It's an interesting example of the template pattern at work. So let's go ahead and see what it does. Let's see what the inputs and outputs of this algorithm are. An article, maybe from a newspaper or a magazine, comes in, and as an output, we want a 3-sentence summary of this article. Let's look at the steps involved one by one. The steps we are going to walk through right now form the template of the algorithm. This clearly defines the template pattern because we are specifying a series of steps, but you as a user don't need to implement all of them. You need to implement just one, the most important one. The very first step is to split the article into sentences. We want the output to be specified in sentences, so we split it into sentences in order to be able to rank them. The next thing we do is to split each sentence into its words. Words make up a sentence, and we split each sentence into its corresponding words and try and gauge the importance of each word in a sentence. We then determine the importance of each word in a sentence. This is a key thing. Note that we don't speak about how a word becomes more important. We just say we determine its importance. Now, the importance of a sentence is the sum of important words in it. So a sentence has a whole number of words. Let's eliminate all the simple ones like a, an, and the. The importance of a sentence is the sum of its important words. The next step is to rank the sentences by their importance. So now we have an importance number associated with each sentence. We can just go ahead and rank the sentences by their importance. And lastly, we return the result, which is the top 3 most important sentences. The algorithm should be very straightforward and clear to you at this point. This is the template. Now, what do we do after this? This is an abstract base class with every step implemented except step 3, determining how a word is important. What determines the importance of a word has not been implemented. This is the hook. Step 3 is left blank as an abstract method, and it's for you as a user to specify what makes a word important for you. Step 3 is obviously a key bit of this algorithm. It basically determines which 3 sentences will come out. It's the nub of the algorithm, as it were. This is what the programmer customizes. Now, you as a programmer could figure out in any manner the importance of a word. For example, you could say that the importance of a word is equal to how often that word appears in today's New York Times front page. That could be your algorithm. Or you could say, I just like some words better than the others, so they are more important. Nothing stops you from putting in any bit of logic that you want. That is the hook. And this together, the template and the hook, is the template pattern. All the programmer has to do is to extend this abstract base class and provide the implementation for exactly one method, step 3. Now, the template pattern is a precursor to the use of frameworks. Frameworks are these huge moving bits with a bunch of libraries and a way to interact with the programmer and get events back from the framework. For this reason, it makes sense for us to conceptually understand frameworks in a little more depth so that we understand the template pattern as a whole. So, onward to understanding frameworks.